Swayam Prabha. Digital India. Educated India.
Hello everyone. Now our present topic is flare leading speed frame, where we will discuss the simplest mechanism which is used for mainly jute and flax spinning system, and how the speed is being controlled and also tension in the thread is controlled. This is actually, this system is used for coarser material, and this is also known as throttle spinning, and where we do not have any additional drive to the bobbin, only flare is giving drive through the spindle, and that rotates at the constant speed, and bobbin speed changes based on the delivery speed, and the bobbin is being pulled by the tension of the thread, that is the yarn or roving. Now, here you can see this is the system here. Now, here twist is the spindle speed RPM by roller delivery, that is same as that of the bobbin leading. As it is flare leading, that means its a flare will rotate at the higher speed. Now, the here system is that this one is the front roller of the drafting system, front drafting roller, and here is a roving, and it goes through the flare leg and up to the bobbin. Now, here bobbin it is shown in the red color, and bobbin is, there is no such drive, no additional drive is given to the bobbin. Bobbin is rotated at by the drag of the roving. Roving actually pulls the bobbin and it follows the flare, and depending on the delivery rate, the lag starts. The lag of the flare, the lag of the bobbin will depend on the delivery rate. Higher the delivery rate, so higher will be the lag. So, the relationship here is that V d equal to pi bobbin diameter multiplied by N f minus N b. This is the relationship here. So, bobbin diameter gradually increases, sorry, this is bobbin diameter gradually increases. So, to maintain the delivery speed, so bobbin speed has to increase. So, that is the bobbin, and this is increased by the increase in drag, and the system here is that bobbin is not like a cotton bobbin. Here bobbin is actually loosely placed on a felt drag, circular drag, annular, this type of central, there is hollow, and here this is a felt drag, and the bobbin has got flange. So, bobbin flange sits on this felt drag or washer, okay. And the lifter motion here, lifter rail moves up and down to have the traverse, and here the traverse rate is fixed. It is not like the cotton roving frame where traverse rate changes, it's fixed, because it's a twisted yarn, twisted roving. So, and thick roving, there is strength is there. So, there is no chance of breakage, and it drags the bobbin and makes the bobbin rotate, okay, by the drag, and it slides over the felt drag washer, and that is why the felt drag washer impart its friction. As soon as it breaks, any breakage takes place, the felt drag washer will stop the bobbin for further rotation. Okay. Now, so winding on, the bobbin fits loosely outside the spindle. Therefore, so this bobbin, you can see bobbin does not have any other motion, it only loosely fits on the outside the spindle. This is the bobbin, it fits outside the bobbin loosely, and it is placed on a felt drag washer. It can rotate freely independent of the spindle speed. It slides up and down because it is a loose fits loosely by lifter rail. The flare is, on the other hand, it is fixed on spindle and revolves at the constant spindle speed. Here only one drive is given, that is only the flare or spindle, it rotates on on a constant speed. The revolution of spindle around the bobbin will wind the delivery length on the bobbin surface. That means, the spindle or flare revolves around the bobbin. So, that is why winding takes place. So, here there is a system, you can see this is the felt drag here, okay, felt drag washer, and here is the spindle, okay, and flare is given. One revolution of the flare, the bobbin surface will be dragged by one round rotation. Okay. So, that means, if there is no delivery, that is length of delivery is 0, that means flare will drag the bobbin of full one revolution. Okay. But as there is a delivery rate, so there it has got certain value delivery rate, that means the effectively bobbin will start lagging. So, for one flare revolution, the bobbin surface will be dragged around less distance than the effective bobbin circumference, which is by the length of bobbin roving delivered. So, you can see here, if there is no delivery and the material is threaded, so for one revolution of the flare, it will drag the bobbin for whole one revolution, but as the delivery is there, so it will start lagging behind that. So, as the bobbin RPM NB increases, spindle RPM remains constant, the winding on RPM will reduce, that is minus 1 winding on RPM. So, bobbin RPM will actually, bobbin has got does not have any positive drive. So, bobbin RPM will be equal to spindle RPM minus the winding on RPM. So, winding on RPM is equal to front roller delivery divided by the bobbin circumference. That is what we have already seen earlier. Now, front roller delivery is constant, bobbin circumference is increasing, that is why the winding on RPM reduces gradually. You can see as it is a flare leading, at the starting point it may not, it is not at 0 point, starting point the bobbin speed will be there and it gradually increases with the diameter of bobbin, and it will never reach the flare speed, because in that case the equation will not be matching. So, during winding on, the bobbin is traversed up and down that bobbin, and then it forms the traversing and by the ring rail, sorry, lifter rail, that here we call it as a lifter rail, it moves up and down at a constant speed. So, winding tension can be calculated, and we can see interestingly the winding tension gets actually the compensated. So, winding tension can be controlled also. Now, try to see here, this is the fail drag. Fail drag is the system which applies the winding tension, which controls the winding tension. Now, let us see, R is the normal force on the felt drag, which is nothing but the weight of the bobbin with the material. So, normal load on the washer by the bobbin weight. R, mu is the frictional coefficient between the washer and the bobbin flange surface. D1 is the inert diameter. So, this is D1 and outer diameter is D2. Inner diameter of washer, D2 is the external diameter of washer. Now, we can see the washer, this is the washer, here it is a D1 and this will be D2, D1 and D2, and frictional resistance can be taken as a acting in the mean radius. So, at the mean point, so it will be basically D1 plus D2 by 4 mean radius as the frictional resistance will be taken. So, torque will be mu r multiplied by the mean radius, which is D1 plus D2 by 4, that is the torque to rotate the bobbin, which is proportional to the winding tension. That means, winding tension is actually responsible to rotate the bobbin, which is actually proportional to the torque, and torque is mu r multiplied by the mean radius D1 plus D2 by 4. Now, D1 is constant, so inner diameter is constant. Now, we can increase the bobbin tension. How can we increase the bobbin tension? If we increase the D2, D1 is constant, because we need a certain D1 because of the, it is a hollow because of the spindle diameter. D1 can, but D2 can be changed. Higher the D2, higher will be the winding tension. So, we can use the larger size washer to increase the winding tension here. So, we can manipulate the winding tension if there is any breakage, higher breakage taking place. In that case, we can reduce the D2 outer size, outer diameter, and if there is a soft package, then we can increase the winding tension by increasing the D2. So, D2, that is the bigger diameter washer, the tension increases, and the vice versa. Okay. And if it is winding tension reduces, if it increases, if it is reduces. Okay. Now, tension as the bobbin fills, because as the bobbin gets filled, the mass of the bobbin increases. So, as the mass of the material R increases, the winding tension increases due to increase in torque. That is a very simple one, but here some compensation takes place. Now, let us see how. At the same time, there is an increase in effective bobbin radius. So, effective bobbin radius increases. So, you can see here, this is the winding tension and this is radius, here radius R1, R after certain time the T dash and here T double dash. So, we can see here, as the bobbin diameter increases, the mass increases, the resist R increases. So, increase in torque, winding tension increases, but at the same time, if you see the torque, torque is nothing but tension into R, T into R. So, T and T dash into R dash, T double dash into R double dash. So, here T is a torque required will be compensated by increase in radius. So, if we see the this thing, torque, same torque, okay, same torque. So, x torque we can is a TQ, this is TQ dash, TQ double dash. So, if we consider the same torque, in that case we will see as the R increases, T has to reduce. So, that means as the diameter, effective diameter of radius of the bobbin, effective radius is used for to calculate the torque. So, as the effective radius increases, though tension, effective tension will reduce. So, that means the increase in bobbin diameter, that means increase in the material, that is increase in resistance force R, the winding tension increases, but that gets little bit compensated by effective torque radius, okay, bobbin radius used for torque measurement. So, this is equivalent to an increase in length of lever. This is the length of lever used to pull a bobbin round. So, length of lever increases as the radius increases. So, this results in slow increase in winding tension. So, as the bobbin radius in material on the bobbin increases, so its mass increases. So, it will have higher increase in the tension, it would have normally, but due to the length increase of the lever, this gets little bit compensated. So, the bobbin tension increases with the increase in the bobbin diameter, but to a lesser extent, it slows down. So, you can see in normal case this should be increased, but effective bobbin diameter, the tension increases at the slower rate. due to this lever effect. This is done automatically. Now, we can reduce and increase the bobbin tension by the size of the washer. And apart from this, there is other methods are available. So, in the worsted spinning, we give the roving twist by not by the flare. This is the flare-less roving. It is only rubbing, by rubbing action. Here two the felt drags of that aprons are there. They move in the longitudinal direction just to feed the material. At the same time, they actually moves at the other direction, right angle direction, and they move to and fro, which makes the imparts the false twist. There is no real twist. So, this makes the material softer material, and for long staple we use this, because which will affect the drafting, which it is a very smooth drafting in the ring frame. This is called rub rover, mainly for long staple fiber, worsted spinning it is used, and pair of oscillating aprons roll and compress the roving, that ribbon of fibers, into a round shape, consolidates more cohesive and continuous length. Wound on a package with minimum tension on the tube, there is no such tension. Generally, pair of roving stands are wound on package. So, we do not normally do a single package, because these big packages, it has got very big package we can use here, because there is no limitation of flare and that mass will be higher. And if we use single strand, what will happen? The tension may whatever the tension required, that may not be may be high enough to break the single strand. So, if we use two strands, the low tension is distributed in two strand, so that the roving breakage is not there in ring frame. So, one package feeds the two spindles in ring frame. Now, we will stop here, we will start a new topic in the next class. Thank you.